Welcome back to AI.Code.Cast. Today, we're going to do a deep dive into this coding problem that you see in like a lot of technical interviews.
Yeah,
And it's got some pretty cool real-world applications too.
absolutely.
So the problem is this. You're given an array of numbers
Okay.
from 1 to n
Okay.
with n plus 1 elements.
Okay.
The catch is
Yeah.
there's one duplicate number hiding in there somewhere.
Yeah,
And your mission, should you choose to accept it, is to find that duplicate.
it's a good one.
Yeah.
And what makes this problem really fascinating is the constraints that are often placed on it.
Okay.
So you can't modify the array in place, and you're also limited to using a very minimal amount of extra storage space.
So it's like we're working with like a crime scene. We can't like touch anything.
Exactly.
And we got to find the culprit.
That's a great analogy
Yeah.
with
But-
like limited resources.
yeah, absolutely. And just like a good detective.
Yeah.
We need to start with the basics.
So let's first make sure we understand why we're even guaranteed to have a duplicate in the first place, right? Right. If I have, say, 5 pigeonholes
Okay.
and I try to put 6 pigeons in them,
Yeah.
what's going to happen?
Well, one of the pigeonholes is going to have like 2 pigeons in it,
Precisely.
right?
At least one of those pigeonholes is going to have to double up.
Okay.
That's the pigeonhole principle in action.
I see.
In our case, the pigeonholes are the numbers from 1 to n,
Right.
and the pigeons are the elements in our array.
Okay.
Since we have n plus 1 elements
Yeah.
and only n distinct numbers,
Yeah.
a duplicate is inevitable.
It's got to be there.
Exactly.
Okay. So we know it's there.
Yep.
How do we find it?
Right.
I guess like the most basic way is just like
Yeah.
compare every number to every other number.
That's the brute force approach.
Yeah.
That's usually a good starting point.
Right.
And you can do that by using nested loops,
Okay.
right?
So like one loop inside another loop.
Yeah, one loop inside the other.
Yeah. The outer loop goes through each number,
Uh-huh.
and the inner loop compares that number to every other number in the array.
Okay.
If you find a match,
Yeah.
boom, you found your duplicate.
Okay, great. We found it.
Straightforward to implement, right?
Yeah.
But it comes with a cost.
Okay.
The time complexity of this approach is O of n squared,
N squared.
meaning the time it takes grows quadratically
Mm-hmm.
with the number of elements in the array.
So if my array is like twice as big, it could take like 4 times as long.
Exactly. That's exactly right.
Okay.
If your array doubles in size, the time it takes to find the duplicate could potentially quadruple.
Yeah, that's not good, especially if we have like a really big array.
Exactly. And that's where the fun begins,
Yeah.
finding more efficient ways to solve the problem.
Okay.
What if we tried to impose some order on the chaos?
Okay.
Think about what happens if we sort the array first.
Okay, so if we sort it, then every like similar number will be next to each other.
So we can just look for the numbers that are next to each other that are the same.
That's the idea.
Okay.
Sorting simplifies the search for duplicates.
Yeah.
However, we need to consider the cost of sorting itself.
Oh, right. Yeah.
Most efficient sorting algorithms
Yeah.
have a time complexity of n log n,
Okay.
which is better than n squared,
But still not great.
but still not ideal.
Okay.
Um,
So sorting helps, but it's not like the perfect solution.
it's not a silver bullet.
Yeah, what if we tried something completely different?
I
Like,
get it.
could we somehow use the array itself to keep track of the numbers we've already seen?
That's a great thought.
Yeah.
It reminds me of a technique called negative marking.
Okay.
We can exploit the fact that all our numbers are positive.
They're all positive.
Think about it. What if we could use the sign of a number to indicate whether we've encountered it before?
Oh, like plus or minus.
Yeah.
Exactly.
Okay, I'm listening. So for each number in the array, we can use its absolute value as an index.
Mm-hmm.
We then check the sign of the number at that index. Got it? It's positive.
Yeah.
We flip it to negative,
Okay.
marking it as seen.
Got it.
If it's already negative,
Yeah.
we know we've found our duplicate.
So like if the number 3,
Yeah.
we go to the index 3 in the array.
Yep.
And if it's positive, we change it to -3.
Exactly.
But if it was already -3, then we know that's our duplicate.
You nailed it.
Okay.
It's a clever way to use the array itself as a tracking mechanism.
Okay, cool.
This approach gives us a time complexity of O of n,
Which is linear.
which is linear and much faster than the brute force method for large arrays.
That sounds pretty good linear time.
It does, right?
But I bet there's a catch.
Well, there's always a catch.
Yeah.
It does modify the original array,
Okay.
which might not be acceptable in all scenarios.
Right.
Also, it relies on the assumption that all the numbers are positive.
Right. If they're all negative, this doesn't work.
Exactly.
Okay.
Good point.
So we have a trade-off here.
Yeah. Better time complexity, but it changes our array.
That's right.
I'm curious to see if there's other approaches that can like find the duplicate But without changing the array.
There are indeed.
Oh.
There are indeed. We'll explore some of these alternative approaches in the next part of our deep dive,
Okay.
where we'll venture into the fascinating realms of binary search and cycle detection.
Oh, that's cool.
Yeah.
Okay, stay tuned. Welcome back to AI.Code.Cast. Last time we were talking about,
The duplicate number problem.
yeah, the find the duplicate number problem.
Yeah.
And we talked about, like, the brute force way.
Right.
And negative marking. And we were wondering if there's a way we could find the duplicate without changing the array at all.
Yeah, without modifying the array.
And you hinted at using binary search, which is usually on a sorted array.
Right.
But our array isn't sorted.
Exactly. So how do we apply binary search here?
Yeah.
Well, that's where things get really interesting.
Okay.
While the array itself isn't sorted.
We can use binary search on a different property.
Okay.
The count of numbers less than or equal to a given value.
Okay, so like how many numbers are less than 5?
Exactly.
Okay, and how does that relate to binary search?
So imagine we pick a number mid
Okay.
within the range of possible values, 1 to n.
Okay, 1 to n, got it.
We then count how many elements in the array are less than or equal to mid.
Okay, so like if there's no duplicates, that count should be mid, right?
Yeah, got it.
Okay.
But here's the key. If there's a duplicate,
Yeah.
the count will be higher than mid.
Right, because there's like an extra number in there.
Exactly.
Okay.
That discrepancy tells us which half of the search space to explore next.
So if the count is higher than mid, then we know the duplicate has to be between like 1 and mid.
Exactly.
But if it's not, then it's got to be between mid plus 1 and n.
You got it.
Okay.
We keep having the search space based on this count until we pinpoint the duplicate. It's a bit like playing a number guessing game where you get clues about whether the secret number is higher or lower than your guess.
I like that. Okay, cool. So we're not searching for the actual number. We're searching for like this count.
Exactly. We're using the count as a proxy.
Okay, that's cool. What's the time complexity of this?
So it's O of n log n.
Okay.
Similar to sorting, we have a logarithmic factor from the binary search and a linear factor from counting the numbers less than or equal to mid in each step.
Okay, so it's kind of like the same as sorting.
It's in the same ballpark, yeah.
Okay. What about the space complexity? Do we need extra storage for this?
That's the beauty of it. We only use a constant amount of extra space,
Okay.
making it O of 1.
So no matter how big our array is, we don't need to add any extra space.
That's right. No matter how large the array gets, we're not using any additional data structures.
Okay, so this is pretty good then.
It's pretty efficient, yeah.
But you also mentioned this other approach earlier.
Right.
Something about a tortoise and a hare.
Yeah, the tortoise and the hare.
Like a fable?
It does have a certain fable-like quality to it.
Right.
This approach is known as Floyd's tortoise and hare algorithm.
Okay.
It's a classic technique for detecting cycles in linked lists.
Okay.
But the surprising part is how we can apply it to our array problem.
Okay, how do we make an array a linked list?
We don't actually create a new data structure. It's all about how we interpret the array. Imagine each element in the array as a node in a linked list, where the value of the element points to the index of the next node.
Okay, so like if index 3 was the number 5,
Yep.
then it points to index 5.
Exactly.
Okay, got it.
Now, because we have a duplicate number in the array, this imaginary linked list is guaranteed to have a cycle.
Okay.
The duplicate acts as the entrance point of this cycle.
Oh, okay. I'm starting to see this.
Now imagine the tortoise and hare racing along this linked list.
Oh, wait.
The tortoise takes one step at a time,
Okay.
while the hare, being much faster, takes
Yeah.
2 steps at a time.
Got it.
Because there's a cycle, they are bound to meet somewhere within that cycle.
Okay, that makes sense.
Right.
But how do we know where the cycle starts?
That's a great question. Just knowing they meet doesn't tell us where the cycle begins.
Right.
We need to find the duplicate, which is the entrance point of the cycle.
Right, exactly.
That's where the second phase of the algorithm comes in.
Okay.
Once the tortoise and hare meet,
Yeah.
we reset the tortoise back to the beginning of the linked list,
Okay.
which is index 0 of our array.
Got it.
The hare stays at the meeting point.
So now they're both going one step at a time.
Exactly. Now they're moving at the same speed.
Okay.
And here's the magic: they will inevitably meet again. And this second meeting point will be the entrance of the cycle, which is our duplicate number.
Wait, hold on. So we make this fake linked list, and then the hare and the tortoise race, and then wherever they meet is our duplicate number.
The second time they meet
Oh, the second time they meet.
is the entrance to the cycle, which is our duplicate number.
Okay, I think I'm following this, but how does that actually work?
It all comes down to the distances involved, the distance from the starting point.
Index 0.
Index 0 to the cycle entrance is the same as the distance from the first meeting point to the cycle entrance.
So by moving at the same speed, they're both going to cover that distance,
Exactly.
ended up at the beginning of the cycle.
You got it. Floyd's tortoise and hare algorithm is a clever way to exploit the structure of the problem.
Wow. Okay, this is cool.
Yeah.
So we went from brute force to like binary search to like tortoise and hare. This is awesome.
It's a journey.
Yeah. What's the complexity of this one?
The time complexity is O of n.
Okay.
Just like the negative marking approach.
Right.
We traverse the array a few times at most.
Wow.
And the best part, the space complexity, is O of 1.
So constant space.
Constant space.
Wow. So it's the best of both worlds.
It's very efficient.
Yeah. It's incredible how many ways we can solve this problem.
Yeah. That's the beauty of algorithms. There's often more than one path to the solution, and each path offers unique insights and trade-offs.
Yeah. I feel like we've gone on an adventure through the world of algorithms today.
We have.
From brute force to binary search to the tortoise and the hare.
It's been quite a journey.
Yeah. And like not only have we learned the algorithms, but we've also learned like the principles behind them.
Absolutely. And what's important is not just memorizing the steps, but understanding the underlying principles. The pigeonhole principle,
Right.
the concept of monotonicity,
Uh-huh.
the power of abstraction, and the elegance of cycle detection.
Yeah, these can be applied to so many other problems.
Exactly. They transcend this particular problem.
So next time we see a hard problem, we should just remember this problem.
Remember the duplicate number? It might just inspire you to think outside the box and find a truly elegant solution.
I love that. Welcome back to AI.Code.Cast. We're wrapping up our deep dive on the find the duplicate number problem.
Yep.
We've already seen like some really cool solutions like negative marking and even using binary search in a weird way.
Yeah, in a surprising way.
Yeah, and we just started talking about this Floyd's tortoise and hare algorithm.
Right, which uses this concept of cycle detection.
Yeah, but before we move on, I'd like to see this in action. Like,
Yeah, absolutely.
could we go through an example?
Let's say our array looks like this one, 3, 4, 2, 2.
Okay, so we have 5 elements and the duplicate is 2.
Yep.
Now, how do we make this into our like imaginary linked list?
Remember, each element's value points to the index of the next element.
Okay.
So we start at index 0, which holds the number 1.
Right.
This tells us to go to index 1.
Okay.
At index 1, we find the number 3, so we go to index 3.
Got it.
And so on.
So it goes like 1, 3, 2, 4, 2, and then back to the 2.
You got it, and then it cycles back to the
Right.
second occurrence of 2.
Okay, so we got our linked list.
Now let's introduce our tortoise and hare.
Okay.
Both start at index 0. The tortoise takes 1 step, moving to index 1, the value 3. The hare takes 2 steps, landing at index 3, the value 2.
Okay, so here's going faster.
The hare's much faster.
Okay, and then eventually they're going to run into each other.
Precisely. In this case, they'll meet at the second occurrence of the number 2.
At the 2, okay.
Now for the second phase of the algorithm.
Okay, so we put the tortoise back at the start,
Back to the starting line, index 0.
and the hare stays
The hare stays put.
where it is.
Yep.
Okay.
Now they both move 1 step at a time.
Got it.
The tortoise goes from index 0 to index 1, and the hare goes from the second 2 to the number 4.
It's a 4.
And in the next step, the tortoise moves from index 1 to index 3, the first 2, and the hare moves from index 4 back to the second 2, which is their meeting point.
So they meet at the 2 again,
They meet at the 2 again.
which is the duplicate.
Exactly. And the second meeting point is the entrance to the cycle, which is our duplicate number 2.
Okay, wow, it actually works.
It's pretty neat, right?
It's great.
It's a simple concept, but it leads to a very elegant solution.
Yeah, I like that a lot. So now we have this new tool, the Floyd's tortoise and hare.
Add it to your algorithmic toolbox.
Yeah, exactly. And it can solve more than just this problem.
Right. The core principle of cycle detection can be applied to a wide range of problems, not just finding duplicates in arrays.
Cool. So we've gone from brute force to cycle detection.
The whole gamut.
Yeah, the whole thing.
We've analyzed different approaches, discussed time and space complexity.
Hopefully you learned something new today.
Absolutely. And hopefully you've gained a deeper appreciation for the beauty and creativity of problem solving in computer science.
That's all for today's episode of AI.Code.Cast. Until next time, keep those coding skills sharp.
And don't be afraid to think outside the box.
See you later.